Hello, I'm Dhanush, and this video is going to be about Schrodinger's wave equation. In this video, we'll be discussing about Schrodinger's wave equation, and we'll be deriving the time-dependent and time-independent wave equation. This wave equation is a partial differential equation which uses the concept of energy conservation to obtain information about the behavior of an electron bound to a nucleus. Schrodinger's wave equation gives us the value of psi, electron's wave function, which is associated with two parameters, which is the position x comma y comma z and time. With this psi, we can find psi square, which is the probability density of finding an electron. The more the value of psi square, the more the likelihood of finding the electron at that point, and vice versa. For its lesser. Before deriving Schrodinger's time independent and dependent wave equations, let's consider the following assumptions. De Broglie wavelength can be applied for the matter waves for any field of force. Based on this, the total energy of particle can be written as total energy is equal to potential energy plus kinetic energy, or E is equal to V plus half mv square. You know, the equation of kinetic energy is the potential energy and total energy, which can also be equal to V plus p square by 2m. Kinetic energy can also be written as p square by 2m, where p is the momentum, and we know p momentum is equal to mass times velocity, and from this we can get p is equal to 2m. But we know that de Broglie wavelength lambda is equal to h by p, so this would imply lambda is equal to h by root over 2m into E minus V. This is the final equation. Let this be equation number 2 and this be equation number 1. Now this is the first assumption. Let's move on to the next assumption. The wave function associated with the material particles with the function of time t can be written as psi is equal to psi naught into e power minus I omega t, where psi naught is the amplitude of the wave at point x comma y comma z, and angular frequency omega is equal to 2 pi nu, where nu is the frequency of radiation. So this is the second assumption. Let this be equation number 3. Now let's derive Schrodinger's time independent equation. Let us consider a system of stationary waves associated with the moving particle. Let psi be the wave function of the particle along x, y and z coordinates at time t. The differential wave equation of a progressive wave with wave velocity u can be written in terms of Cartesian coordinates as this: d square psi by dx square plus d square psi by dy square plus d square psi by dz square is equal to 1 by u square times d square psi by dt square. Let this be equation number 4, and let the solution for the equation 4 is the equation 3. So differentiating 3 with respect to time, we know equation 3 is psi is equal to psi naught into e power minus I omega t. This is equation 3. So differentiating it with respect to time, this is equal to psi. Now if we double differentiate it, we get Let this be equation number 5. D square psi by dt square is equal to minus omega square psi. Now if we substitute equation 5 in 4, we'll get is equal to minus 2 pi nu whole square by u square into psi. So which in turn implies that d square psi by dx square plus d square psi by dy square plus d square psi by dz square is equal to minus 4 pi square nu square by u square into psi. Now substituting the wave velocity u, which is equal to nu lambda, we get, and let this be equation number 6. So substituting it, we get d square psi by dx square, d square psi by dx square plus d square psi by dy square plus d square psi by dz square is equal to minus 4 pi square nu square by lambda square nu square into psi. So d square psi by dx square plus d square psi by dy square plus d square psi by dz square is equal to minus 4 pi square by lambda square nu. Let this be equation number 7. Now if we substitute equation number 2 in equation number 7, we get substituting equation 2 in 7, psi by dx square plus d square psi by dy square plus d square psi by dz square is equal to minus 4 pi square by h square into 2m into capital A minus v into psi. But we can take this as we know that delta square is and let this be equation number 8. So we know psi square, this is known as the Laplacian operator. So with the help of this we can write equation 8 as and let this be equation number 9, and we can further simplify this as where this is equal to h by 2 pi. Therefore this is the Schrodinger's time independent equation. These both are Schrodinger's time independent equations. Now let's move on to proving Schrodinger's time dependent equations. From Schrodinger's second assumption, we get equation 3, which states that psi is equal to psi naught into e power minus I omega t. Differentiating with this, we get d psi by dt, which is equal to minus I omega psi, which is equal to minus I 2 pi nu psi. And we know that E is equal to h nu. E stands for energy. So we can write this equation as minus I. So which implies E psi is equal to minus h by I d psi by dt. As we know, h by 2 pi is equal to this. And we can further simplify this as E psi is equal to I d psi by dt. Let this be equation number 12. From Schrodinger's time independent equation 10, which is substituting E psi, we get multiplying equation 13 by let this be equation 13. If we multiply this by this quantity, we get let this be equation number 13. Multiply equation 13 with this quantity. So we get or let this be equation number 14. So this can be written as and let's be equation number 15. Here h is the Hamiltonian operator. Therefore h psi is equal to E psi. This will be equation number 16. Equation 14 and 16 are called Schrodinger's time dependent wave equations. And thus we can conclude this video.